Okay, so this upcoming week, we will be going over the rest of our first module. So we're going to be looking at heating and cooling curves. As well as we're going to look at vapor pressure. And phase diagrams. So those are our big things we have left in our first module. For our second module, we will be going into solid. And I've got it set as a 1-day lesson. And we'll see how that works. Sometimes that works great, sometimes it doesn't. We're not going to go super far into solids, but when we get into solids, we're going to be looking at a lot of the stuff we're going to be looking at in lab. So we're going to be looking at unit cells. We're going to look at just the idea of crystalline solids. And then we're also going to be looking at alloys and semiconductors. Oop. Okay, so let's go ahead and start out by looking at heating and cooling curve. So we looked at it a little bit already. We looked at a heating curve last class. A cooling curve is going to be the opposite. It's going to start out at high temperature, then we're going to kind of level out, and then it's going to keep cooling, and then level, and then cool again. Over here, we're going to have our gas. Here we have gas to liquid. Here we have our liquid, and then liquid to solid, and then lastly our solid. So right here is going to be our evaporation or boiling point. Down here is going to be our melting point or freezing point. With a heating curve, all of our energies should be positive because it's absorbing heat. And then with our cooling curve, this, we're going to be releasing heat. So this is going to be negative. So we're going to have negative energies. Okay. So that's the real difference between our heating and cooling curves. The numbers will be identical if we're dealing with the same amount of mass of substance and we're changing between the same temperatures. So if we're going from -5 up to -5 degrees Celsius up to positive 105 degrees Celsius for 50 grams of water, that heat absorbed will be the same heat as if we're going from 105 down to -5 for that same mass, but it will just be an opposite sign. Anytime we have with either of our curves, heating or cooling, if we have a non-zero slope, so the non-zero slope, the ones that are going up or down, right? Then in those cases, that's where we're changing temperature in one phase. And in that case, we're going to use the equation Q equals mc delta T, or MCAT. So our mass times by our specific heat times by our change in temperature. If we have a zero slope, so when we're not changing temperature, it's flatlining, those are our phase changes. And in those cases, we're going to use Q equals generally moles times by our enthalpy of state change. But you really need to pay attention to the unit here. It's usually in kilojoules per mole. So delta H is usually in kilojoules per mole, so we need to have our unit of amount in moles. With specific heat, this is generally in joules per mole times by degrees Celsius or Kelvin. Either one is the same exact thing. But in this case, sorry, not moles. Oh my goodness, I put the wrong thing. Joules per grams times by degrees Celsius. So in this case, generally this specific heat is given in grams, so we're going to have our amount in grams as well. Oops, sorry. Another thing to note, this is generally in joules, this is generally in kilojoules, so we're going to need to transform one to the other, or from one or the other. From one to the other? That's probably right. Last thing to note about this, our delta T, this is always T final minus T initial, so make sure you're putting your final temperature in and subtracting your initial temperature. If you're increasing in temperature, your final temperature would be higher than your initial temperature. If you're decreasing, your final temperature would be lower, and you'll have a negative delta T. With our phase changes, if we're going from a solid to a liquid, we're going to use delta H of fusion. If we're going from a liquid to a solid, we're going to use the negative delta H of fusion. If we're going from a liquid to a gas, we're going to use delta H of vaporization. If we're going from a gas to a liquid, we're going to use negative delta H of vaporization. As because when we go to solid to liquid, that requires energy. Liquid to solid releases energy. Okay, so that's the first thing. We're going to very briefly talk about the idea of equilibrium. And we're just going to compare it to equations, chemical equations we've looked at so far. So usually when we think about a chemical equation, we have A going to B. So this is what we call a one-way reaction. And we're going to react until we run out of reactant. With an equilibrium, we have A going to B, but then we see this two-way arrow, so that means we have B going back to A. So this reaction has a forward direction, and it has a reverse reaction. The forward reaction is A going to B, the reverse is B going back to A. So in this case, we never reach a point where we go to all reactant or all product. We are somewhere in between the two. And for right now, all we're going to really look at is just the idea of an equilibrium. And the reason we do this is because when we're thinking about a phase change, if you are talking about you're at 100 degrees Celsius, for instance, if you are exactly at 100 degrees Celsius, your liquid state is going to be in equilibrium with your gas state. So you're going to have both liquid and gas state at the same time if we're in a closed container. If you're not in a closed container, then things can't really get to equilibrium. But if you have a closed container and you're at that 100 degrees Celsius, you will be in equilibrium between those two states. So you have some amount of liquid, some amount of gas. If you heat up beyond 100 degrees Celsius, you're going to shift more towards your gas. Cool down a little bit below 100 degrees Celsius, you're going to shift more towards your liquid. So right now we're just looking at equilibrium in terms of phase changes, but we will move on in a couple modules to look at equilibrium in terms of real reactions. So we're just bringing up the idea of equilibrium right now, as it's usually a pretty new topic for people. But yeah, okay. So that's our next topic that we're going to go over tomorrow. Our last kind of two, we have vapor pressure. So our vapor pressure is the pressure exerted by a vapor. Can't spell. The greater the amount of your substance that's in the vapor phase, the greater the vapor pressure. So more substance in the vapor phase, greater vapor pressure. And this is something that if we have a closed container, we'll always have an equilibrium vapor pressure. So if we think about taking like a beaker of water. And we put a lid on top of that. If this is left for a certain amount of time, there will be liquid water going into the gaseous phase and gaseous water going into the liquid phase. So they'll be in equilibrium with each other. So our liquid and our gas will be in equilibrium with each other. Even if we're not at 100 degrees Celsius, there'll be some amount of liquid in there. Since if we're talking about room temperature, there's not going to be a lot of gaseous water, but there's going to be some amount. And we probably kind of understand that there's some amount of water in the air. We live in a very humid area. So we understand that, water in the vapor phase is a thing. And as you increase kind of the moisture, you increase the amount of, or the amount of, liquid in the area, you increase the amount of liquid that happens to be in the gaseous phase. That's why it gets so humid. But they're going to be in equilibrium with each other. And if we were to heat this up, we're going to shift this more towards our gas phase. So our vapor pressure is going to increase as we increase temperature. And then if we think about substances that all have the same, or are all at the same temperature, they will not have the same vapor pressure. Substances that have very strong intermolecular forces are going to be more likely to be in the liquid phase, because those intermolecular forces are going to hold those molecules in the liquid phase, and they're going to have very low vapor pressure. So strong intermolecular forces are going to lead to low vapor pressures. And then the opposite will be true if we have weak intermolecular forces. Weak intermolecular forces, the molecules aren't going to be as attracted to each other, and they're going to be more easily able to get into the vapor phase. So that means that if we have weak intermolecular forces, we're going to have higher vapor pressures than things with stronger intermolecular forces. So water, for instance, is going to have pretty low vapor pressure. It's not considered what we think of as a volatile substance, a substance that easily goes into the vapor phase because of those strong intermolecular forces. But something like acetone, which is the main component in nail polish remover, that has weaker intermolecular forces. And as a result, it's going to have a greater vapor pressure. Perfumes are another good example of substances that usually have pretty high vapor pressures because they have weaker intermolecular forces. And those two I named specifically because they're ones that we know are in the vapor phase because we can smell them, right? So if you've ever gone to a nail salon and you've had someone take off the nail polish, go into a nail salon, it just smells like acetone. And that's because acetone has a strong or has weak intermolecular forces, so it has a high vapor pressure, so it goes into the vapor phase really easily. Perfumes, they choose compounds that smell pleasant and that vaporize easily, so that when someone walks by, you can smell their floral pretty smells. Same thing with cologne, I guess. They're manly smells. So yeah. Okay. So vapor pressures are going to increase with weaker intermolecular forces, and they're going to increase with higher temperatures. We can relate our vapor pressure for a substance with the energy that's required to get it into the vapor phase, or the enthalpy of vaporization, using what's called the Clausius-Clapeyron equation. Or Clausius. I have to look at how to spell that. So our Clausius-Clapeyron equation, this is going to relate vapor pressure with enthalpy of vaporization. So the equation is a natural log of vapor pressure at one state. The equation I have here is 2 divided by P1 is equal to negative delta H vap divided by T 1 over T2 minus 1 over T1. And we could switch the 1 and 2, it doesn't really matter. But P1, this is our vapor pressure. At T1, which is going to be in Kelvin. And then obviously P2 is going to be our vapor pressure at T2. And again, that's going to be in Kelvin. Oh, excuse me. I am missing. This is not a T on the bottom here. This is supposed to be an R. Our delta H vap, that's our enthalpy of vaporization. Which is generally given in kilojoules per mole. And then our R is our gas constant, the 8.314, but we're going to want to use 0.008314, as that's our kilojoules per mole Kelvin. That way we keep our units the same, keeping them both in kilojoules. Let me try and rewrite that. That's kind of hard to see. Okay, So we'll look at using some problem or working through some problems using those or using the Clapeyron equation. Last thing that we're going to be going over from this first module, so the last thing we'll go over on Tuesday, is a phase diagram. So a phase diagram, we're looking at what phase of matter we're in at specific temperatures and pressures. So on our bottom axis, we're going to have temperature. And then on our y-axis, we're going to have pressure. And the units, they're usually atmosphere and degrees Celsius, but sometimes you might see them in millimeters of mercury and Kelvin, or torr and Kelvin, or all sorts of different ones. As long as you're consistent, it doesn't really matter. So essentially, with this, you're going to have what almost looks like a little Y, like this. At our lowest temperature is going to be our solid. And then at our lowest pressure is going to be gas. And then the one in our V in the middle is going to be our liquid. So each of these lines, so this line right here, oops, this line right here, this is our line that represents the equilibrium between our solid and our gas. This line right here represents the equilibrium between our solid and our liquid. And then this one right here represents our equilibrium between our liquid and our gas. This point right here is called our triple point. And at that specific temperature and pressure, we have all three of our states in equilibrium. Up here, we have another kind of little Y. This point right here is called our critical point. And our critical point is the last point where we can have a distinct liquid and gas phase. Any temperature and or pressure above that point, we are in a supercritical fluid. That supercritical fluid is going to be a state where we're somewhere between a gas and a liquid. We can dissolve things like a liquid, but it has a density closer to a gas. It has the ability to diffuse through things like a gas. But yeah, so it's kind of a weird state. It kind of like moves a little bit like a liquid, so it's really, really weird. Additionally, another thing that we will see when we are at 1 atmosphere, so kind of the last thing on here, if we are at 1 atmosphere, we can see where our normal melting point is and our normal boiling point. So this right here would be our normal melting point. Which is literally just the melting point when we're at a pressure of 1 atmosphere. And then this one right here is our normal boiling point. Which is our boiling point when we have an atmospheric pressure of 1 atmosphere, which is the most normal one. There are species like carbon dioxide that don't have a normal melting or boiling point. They only have a normal sublimation point. So we go directly from our solid to our gas. So Most substances, however, will have normal boiling points and normal melting points. Okay, so that is everything that we're going to be going over on Tuesday. Do you have any questions about any of that? And you can type them if you would prefer. Okay. Oh, there is a question. There we go. Yeah, perfect. Excellent. Okay. Next, we are going to look at solids. So most of this we're going to be going over in lab on Tuesday and Wednesday for our class. But we're going to kind of briefly go over the topics right now as well. So we're talking about a solid. A solid can either be amorphous or it can be crystalline. An amorphous solid is one that lacks a repeatable structure. And then a crystalline solid is one that has a repeating subunit that goes throughout the entire solid. Which we call a unit cell. And it's throughout the entire solid. So this one unit cell is repeated over and over again in all three dimensions. An example of an amorphous solid versus a crystalline solid, cotton candy would be an amorphous solid. And then something like rock, the kind of like the rock sugar things would be a crystalline solid. So when you have the little sticks where it's a bunch of sugar, all of that was grown slowly, and that slow growth allowed that sugar to form that crystalline solid. With the amorphous cotton candy, sugar is heated and then cooled super quickly to get kind of that flossy look. So you can see visually the difference between those two structures by the fact that, your cotton candy looks like this, and then your crystalline solid has like your rock salt or whatever it is, has those kind of crystals within. I'm not doing a very good job of drawing crystals, but let's pretend that those are crystals. And that would be our crystalline solid. So amorphous versus crystal. Let me see if I can find a picture of that. One bit. So this is that rock, or where I don't even, rock candy. And then these are our cotton candy. We can see kind of the difference in their structures. We can see these are crystals that kind of all grew off one point, and then this is kind of flossy where it was just kind of like thrown together. So this is our amorphous solid versus our crystalline. Okay. So when we think about solids, we're gonna essentially just look at our crystalline solids. We should know that an amorphous solid lacks a repeatable unit. It might have some crystallinity throughout, like some polymers will have some crystalline areas, but in general, the overall structure lacks any sort of uniformity or symmetry. So our types of solids are going to be based on what substances make them up. So we have ionic solids. This is going to be made up of cations and anions. And we can have something like sodium chloride would be an example. These ionic solids are going to be very high melting, but they're going to be non-conductive, and all the ions are going to be held together by ionic bonds. We also have metallic solids. In here we have metal cations in an electron sea. But essentially, this is just a bunch of metal atoms. So this in particular right here is the bonding model that we look at, but it's composed of a bunch of metal atoms. And it's going to be held together by metallic bonds. An example of this would be something like an iron solid. These have pretty variable boiling points, melting points. I'm talking about solids. Pretty variable melting points because of this electron sea model that we'll talk about in just a second. So they're going to kind of be all over the place in terms of melting points. Usually they're going to be solids at room temperature, though. There is only one liquid. There's only one liquid metal, which is mercury. But we have some really low melting metals like gallium. If you hold it in your hand, it'll melt. And then we have things like tungsten that are out at like 3,500 degrees Celsius. So huge range of melting points here. These are also conductive. So ionic solids are non-conductive in the solid state. Metallic solids are conductive in this solid state, which is why we make copper wire, or where we make wires out of copper, electronics out of gold and silver and stuff like that. Then we also have our next type of solid is a molecular solid. A molecular solid is when we take covalent species like water or carbon dioxide, and we put it into a solid state. So with these, the atoms of the molecule are held together by covalent bonds, but the molecular solid itself is held together by intermolecular forces. So solid is held together by intermolecular forces. So what we were talking about in this first module. Ionic solids, that solid's held together by ionic bonds. Metallic solids, that solid's held together by metallic bonds. Those are both bonds. So generally ionic solids and ionic solids have really high melting points. Metallic solids tend to have high melting points. Molecular solids, on the other hand, are going to have really low melting points because they're not held together by bonds. They're only held together by electrostatic interactions. So they're going to be the lowest melting of all of our solids. And also this is a molecular solid is composed of molecules. There we go. So a molecular solid is a bunch of molecules. Each molecule is held together by intermolecular forces. Sugar makes a molecular solid. Each sugar unit is a molecule, and then the sugar units are held together by hydrogen bonding. Our last type of solid, and the most kind of the newest solid that we're going to look at, all the rest of them we've kind of discussed a little bit. The last one is called a covalent network solid. So our ionic solid, this is what's called an extended solid. It keeps going on and on and on. So each sodium is surrounded by chlorines. Each chlorine is surrounded by sodiums. So the bonds we just keep going on with more and more bonds, and that's it. Metallic solids, same idea. It's another extended solid. So we have metal atoms bonded to other metal atoms beyond count. Molecular solids, those are discrete molecules held together by intermolecular forces. So not an extended solid. It is a solid that contains discrete molecules. The difference between a covalent network solid and a molecular solid, they both contain covalent bonds, but our entire structure is covalent bonds. So it's another thing that kind of goes on and on again, on and on and on. So this is another extended solid. And it's composed of non-metal or metalloid atoms. That are held together by covalent bonds. So this is going to be another really high melting solid. Another thing that we'll kind of talk about in class on Thursday, our metallic solids are going to be ones that are considered malleable or ductile, so you can kind of stretch them and you can kind of beat them into shape. All of the rest of our solids are really considered brittle solids, so they break they're hard solids, but you can kind of break them apart. So if you think about like sugar or salt, which would be examples of molecular solids and ionic solids, you can grind those up in like a grinder. So I've seen like sugar grinders or mostly salt grinders, but you can grind it down into little particles really easily. You can't really do that with a metallic solid. It's too malleable for that. So those other two solids are really brittle. Covalent network solids, a good example of a covalent network solid would be silica dioxide, which is glass. Well, specifically crystal. Glass is usually an amorphous solid, but if we're talking about crystalline silica dioxide, which is taking a glass and making it crystal instead. So crystal is the crystalline form of glass. With that, it's really easy to break it, right? Again, it's really hard. It's a hard solid, so if you hit it, it's going to hurt a lot, but it shatters reasonably easy because of that brittle nature. So the only one that's at all kind of flexible is our metallic solids. And that's why they are considered both malleable and ductile. Ductile is the ability to draw it into a wire. Malleable is the ability to like beat it into a shape. And both of those things, if we try to do them with any of the rest of the types of solids, they just shatter. Okay, so that's our types of solids. Next topic is going to be our unit cells. I'm not going to go too far into this right now because it's a pretty big topic. But unit cells, this is the repeating unit in a crystalline solid. So there are many different shapes of unit cells. They can be a cube, they can be a rectangle, they can be a little bit more hexagonal. So there's all sorts of different shapes for these. We are going to focus on cubic unit cells. So even though there's 5 total unit cell shapes, we're going to focus on the cubic ones. Cubic ones are exactly what it sounds like. It's a cube, right? So we've got a cube. Dun, 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 dun. And this is our unit cell. And it's got atoms within it. So for instance, we can have atoms on our corners. So this is our unit cell. These atoms, or this unit cell, would be repeated over and over and over and over again. We have 2 kind of like overreaching types of unit cells. We have metallic unit cells, and we have ionic unit cells. Those are the ones we're going to focus on in class and in lab. Those are not the only types that there are, but those are the ones that we are personally going to focus on. With a metallic one, this is going to be all the same atom type, and they're all going to be metals. With an ionic, this is going to be composed of cations and anions. Our anions are going to make up our unit cell. And then we're going to have cations in the kind of leftover spaces, the empty spaces where the anions are not out. So we call these cation holes. So cations are in cation holes. And we'll look at, again, very briefly, each of these. We're not really going to look at the calculations for this. We'll do that in class. But I'm going to just take a picture of what these look like real quick. Because trying to draw these will not work. At least not for me. Oops, that didn't look right. Here we go. Here are our 3 types of metallic unit cells. So these are all metallic unit cells. On our left, we have what's called a primitive unit cell. Center is called a body-centered unit cell. And on our right, we have what's called a face-centered unit cell. So with our primitive, we only have atoms on the corners of this box. So only corner atoms. Our body-centered, we have corner atoms and a body piece. And then our face-centered, we have corners and faces. As in, each face of the cube has an atom. As a note, this is, again, we're talking about the idea that it's an extended solid, so this unit cell is being repeated over and over again in all 3 dimensions. So each of these corner atoms are actually shared with other unit cells. Specifically, a corner atom is shared with 8 unit cells, meaning each time we have a corner atom, that only accounts for 1/8 of an atom. In that case, if we have 8 atoms and each one of them is only an eighth, we would say that our number of atoms in here would be 8, and we give this a Z. That Z indicates the number of atoms. With a body piece, that atom is entirely in the unit cell. It's not shared with any other unit cells. So that's going to be 1 total atom. So this unit cell right here, we have 8 corner pieces. Each one's an eighth of an atom. That gives us 1 atom there. And then we have a body piece. So our Z in this case is going to be equal to 2. So we have 2 atoms total in that unit cell. Our last one, a face-centered. A face piece is going to be, it's on the face. So there's the unit cell that you see it in right now, and 1 more unit cell. So each one of those are going to count for half an atom. There are 6 faces on a cube. So 6 times by a half would give us 3. And then we also have our 1 from our corner. So our Z number in the case of a face-centered cubic is going to be equal to 4. There's more stuff we're going to go over in class. I don't want to go too far into this one because we're already almost an hour in it. I like to have a kind of a molecular model or solid model to talk about. So next thing we're going to talk about, and just very briefly, is the idea of an alloy. So most things that we encounter that have metals in them are alloys. I don't see a lot of pure metals. So alloys are going to be metals plus additional atoms. So we can have 2 different metals together to make a regular alloy, which can either be a interstitial or a substitutional alloy. Or we can make like a metal compound, which is called an intermetallic. Or we can have kind of like different metals or compounds kind of just, or atoms kind of different areas within, which is called a heterogeneous alloy. So I'm going to kind of show you those types. Okay, so these are our different types of alloys. So let's say we have 3 types of metals. If we have a large metal plus a smaller metal, we're going to produce what's called an interstitial alloy. So the little metal will kind of fit in the in-between places of the larger metal. If we have 2 metals that are similar in size, then we get what's called a substitutional alloy, where 1 metal atom will substitute for others of those atoms. We can also form a compound where we have a set. So both of these down here, the ratios vary. But here, this is a compound. So we're going to have a set ratio of the 2 atoms. So this is like a regular compound that we've already seen, but it's entirely made of metals instead of being metals plus nonmetals or all nonmetals. Heterogeneous is where we don't really, everything's not homogenized. So these over here are called solutions because everything's homogenized. Over here, these are compounds because we have set ratios of each atom type. Here, this is heterogeneous because you can just shove things together. And you end up with different phases throughout. So heterogeneous alloys are going to have different phases, or not different. So it is different phases, but different composition throughout. So if we look in this one, we have some iron carbide and some iron metal. So it's kind of fused together. Heterogeneous alloys are usually made a little bit more quickly than interstitial or substitutional. Additionally, with any of these alloys, they don't necessarily have to be just metals. Steel is considered an alloy, and the alloying element we add in there is carbon, and other metals. Okay. Next, we're going to cut really quickly talk about ionic unit cells. So with ionic unit cells, you've got either a cubic or a primitive cubic unit cell or a face-centered cubic unit cell arrangement of anions. So our anions are arranged in either a primitive cubic or face-centered arrangement. So what we saw with the metallic cells. And then our cations fill interstitial spaces. Which are the leftover empty spaces. The reason we do this is our anions are usually larger than our cations. So the cations are going to fit in the spaces. So you think about atoms being spheres. You try and put spheres together, they're not going to be perfectly put together. There's going to be empty space. And since the cations are usually much smaller than the anions, they can fit in those little itty bitty spaces. I'm trying to find the correct image. Oh, yeah, it's right here. Working on this earlier. So these are metals in cation, or are nonmetals in the making up the outer parts. And then, so this is a primitive cubic arrangement. These are both face-centered arrangements. And then in the center here, it looks very much like a body piece, but we call this a cubic hole. If we have the atoms in the corner and, the edges and in the center, we call that an octahedral hole. And then if we have them entirely in there, we call that a tetrahedral hole. So the cations were going, again, in those interstitial spaces. The cubic hole, this is the largest. So this is reserved for the larger cations. Tetrahedral holes are the smallest. So they're reserved for the smallest cations versus the anions specifically. There is one cubic hole per unit cell. There are 4 octahedral holes. So each of the corner pieces are going to account for a quarter of an atom. And sorry, each not corner, each edge. Sorry, each of the edge atoms account for a quarter of an atom, and then that center piece accounts for a whole atom. We have 12 edge pieces. 12 times by a fourth would give us 3. And then the one body would give us our fourth one. With our tetrahedral holes, these are entirely inside the unit cell. We see there are 4 here, 4 here. So there are a total of 8 tetrahedral holes. And I think those are kind of the main things to kind of go over for today. Let me see if there's, oh, the last thing is, sorry, one more thing. Our last thing is a semiconductor. A semiconductor is, these are usually metalloids. Or species that are close to being, they're like somewhere between ionic and covalent. They're like a more covalently bonded ionic species. So they're more covalent in nature. But they're still metals and non-metals together. Their electronegativity differences are very small though. So technically they're metals plus non-metals, but because of their low electronegativity differences, they have more covalent nature to them. So semiconductors themselves, these are somewhat conductive. So if we think about a metal, it's conductive. It conducts electricity without any additional energy. Ionic compounds, true ionic compounds, or molecular species are what we call insulating. So they either require such a large amount of energy to conduct, well, generally that's it. They require such a large amount of energy to conduct that we consider them non-conductive. Semiconductors are in between that. So they need a little bit of energy to conduct, but not a lot. So a lot of times thermal energy in a room is enough to make these conduct. Some require a little bit more. But like silicon, solar cells, they're just made of silicon. Silicon is a metalloid. That is a semiconductor. Cadmium cadmium selenide, which is cadmium and selenium together. That's another semiconductor. That's more of that ionic type. So they all have some conductive nature, and it's all based on their electronic properties, which we'll look at a little bit more. A little bit more in class, but I just wanted to kind of point out that we will be talking about those, but it's not a topic that I think is going to be very difficult for people. Okay, so do you have any questions before we go for today? Okay, excellent. Very welcome. I'll put this video up shortly and have a great day.